Thank you. So hello everyone, and thank you for being here. So this talk will be a bit different from the previous talk that we got, in the sense that it will be really on some geometrical results on a manifold, and this manifold will be endowed with a structure that is related to the Wasserstein distance. And so yes, I will not need to use this. This has already been explained. Of course, you all know that the Wasserstein distance, when it's computed between Gaussian measured, it had already been studied, and we have a nice expression for the distance between two Gaussian measures with given covariance matrices, two centered Gaussian measures. And using the matching between the covariance matrices and the distribution there, this metric there, this distance, can be seen as a distance on the manifold of positive definite matrices. And this is then called the Bure-Wasserstein metric on this manifold, and it has been mentioned several times yesterday in the afternoon. So what we are interested in is the generalization of this to the positive semi-definite case. So assume that the covariance matrices there belong to this manifold, which is the set of positive semi-definite matrices of fixed rank. And so our matrices will be of size n and rank called P. And in that case, it has been shown that the distance associated to this, the Wasserstein distance between those measures is actually the same expression as the one for the full rank case. And similarly, as in the full rank case, this will define a distance on this manifold due to the matching that we have between the covariance matrices and the associated Gaussian distributions. And so this will be the subject of this talk. So we will investigate the geometry of this manifold when it is endowed with the Riemannian metric that will derive in this expression for the distance between the matrices. So the main goal of the talk will be to go to explain you the result that we obtain on the curvature of this manifold. But before this, I will, instead of presenting those results with the proof, I will skip the proof and I will present more generally the geometry with the other tools that we have obtained in previous results. So why are we interested in this manifold? So positive semi-definite matrices and not positive definite matrices, and moreover fixed rank positive semi-definite matrices. Actually, you can see that this manifold has been increasingly used in the previous years. So if you look at the years there of the applications, and it has been used for several topics, including distance learning and role model extraction. So this is for optimization on this manifold. They use algorithm to optimize on this manifold. And curve fitting on this manifold has been used for protein conformation generation, wind field estimation, action recognition, another topic that has been presented in this conference, and parametric model order reduction. And so there are, similarly also to what has been explained yesterday for the positive definite case, several metrics that are proposed on this manifold of positive semi-definite matrices. And here is a quick summary of the expressions that are available. So the research on this topic, on the positive semi-definite case, is less developed than in the full rank case. And so in several cases, we do not have the expression for the exponential and the logarithm, or those expressions are difficult and require to use solver to solve the differential equation to obtain those results. So the one that we will use and that will be associated to the Wasserstein distance is the association of this manifold to this quotient, where this is the set of full rank n times p matrices by the orthogonal group. And you see that the second motivation to use this manifold, and that for this one, we have obtained expression for the exponential and the logarithm. And so we can use them. And so this is useful for numerical applications. So where does this identification come from? Any positive semi-definite matrix can be written like this. So as the product of y transpose, where y is a matrix that belongs to this set. And of course, this factorization is not unique, as you can plug here any orthogonal matrix. So that's where the identification of the two sets comes from. And so we have equivalence classes. So the equivalence class is the set of matrices that are obtained by multiplying the matrix on the right by an orthogonal matrix, and the set of equivalence classes will be defined as our quotient manifold. And it is well known that the two manifolds are diffeomorphic. So as we are dealing here with the quotient manifold, here is just a quick summary of how we usually work with such spaces. So you have our total space, which is here this set, so a set of full rank n-time-p matrices, and you have the fibers, and the fibers will be mapped to our quotient as points. So each fiber becomes a point, and this is mapped through the quotient map. So we will call pi our quotient map. And any tangent vector on the quotient can be represented by one unique horizontal lift in the total space. And those two guys will act similarly as derivators. And one key property here is that this quotient map is a Riemannian submersion. And using this, we will be able to get the expression for the curvature later on. And so before the submission of the paper here to GSI, the available tools on this set were the projection of the tangent space there to this guy on the horizontal and vertical spaces, the exponential map, the logarithm map, and the injectivity radius. And all those have been implemented in the MANOP toolbox. So if you face an application in which you need to use tools on this manifold, you can use the toolbox. And in this talk, we compute the Riemannian curvature tensor, the sectional curvature, and we obtain upper and lower bounds on the curvature. So the motivation to compute those curvatures is the fact that the Riemannian curvature tensor appears in some algorithm for curve fitting on manifolds. So I didn't put the reference here, but it's in the paper. And the sectional curvature is also used in order to compute the step size, is used in order to find a good step size for optimization algorithm on manifolds, and also to obtain results for some curve fitting algorithm on manifolds. So this is for our Riemannian curvature tensor. I just put here the expression. So as I told you, we can compute the projection on the vertical space. We have also expression for this. And so we're able to compute it. The sectional curvature is obtained like this, where here on the numerator, you have the, maybe something I should have said is that the set of this set is endowed with the Frobenius inner product. And so in the numerator, the guy that appears there is the solution of a Sylvester equation. And our goal was to compute the curvature to check whether there were some strange things that appears there or whether it's a nice manifold and we can work on it directly. And the bound that we obtain is that when p is equal to 1, so when the matrices are rank 1, then the curvature is 0. And if p is larger than or equal to 2, the curvature will lie in this interval. So whatever the tangent space, the sectional tangent space, so this is for the sectional curvature, so whatever the tangent space that you will choose, you will be in this interval. And this is interesting because it means that if the matrices are, so those are the singular values of the matrix Y. And so if your matrix is of rank P, but the two smaller singular values are really small, the curvature will explode. So as you reach the kind of border of your manifold, as you will go to the border, but you will have a curvature that will explode at least as if two of the singular values will go to 0 simultaneously. So you have to have two that goes to 0 simultaneously. Okay, so the bonds are tired. So we know that we have tangent plates for which we will get the trouble for the curvature that goes to infinity. And the proof relies on those two results. So those are two lemmas, actually. So first of all, we had to solve the Sylvester equation that appears in the problem. But as here, this equation has some specific structure. So you can see here that you have this matrix that appear on the right and the left. We can diagonalize it. And then this becomes a diagonal equation. And so we get the result quite easily. This comes from a result, actually. This was already known. It comes from a book from Batia. And the second thing was using this inequality. So this inequality is, if you have a 4 there, then it's obvious. Just use the submultiplicativity of the Frobenius norm and the triangular inequality, and you get it. But to get the 2, it's a bit more difficult, and we were not able to find the result in the literature. Maybe it has already been studied, but there are so many inequalities, it was difficult to find it. And so what we have just done is to rederive the result using the optimality condition of the problem. And so that's it. So we have investigated the curvature of the manifold of fixed rank positive semi-definite matrices when this one is endowed with a Riemannian metric that corresponds to the Wasserstein distance. And we have obtained the expression for the curvature tensor and for the sectional curvature. When p is equal to 1, the curvature is 0, and when p is larger than or equal to 2, the sectional curvature will belong to this interval, and so we have here the risk that this goes to infinity as we move to the border. Okay, so that's all for me. Thank you for your attention.
This is very interesting, very intriguing. The thing that strikes me, though, is I would have expected the bound to blow up if the smallest one goes to 0, not the smallest 2.
Yes.
Do you have any insight why? Like you expect when the smallest one goes to 0, right? You're getting close to some variety that is the S of p minus 1 with some sort of a thinner set. And things go bad there.
Yeah.
Now, why 2? That's what...
The 2 appears, I can explain it. I should have a look back to the paper, and I will be able to explain it based on the tools that we have used for matrix theory. But what is true is that the injectivity radius will go to 0 as one of the singular values will go to 0. So as soon as only one of the 2 goes to 0, then your injectivity radius also goes to 0, and so you might have trouble, but due to the injectivity radius then. And so most of the results that use both the injectivity radius and the sectional curvature, those will not be either applicable to this manifold when we go to the border, but due to the injectivity radius. And for the curvature, it's we have to get 2 that goes to 0.
So kind of you cannot distinguish. Yeah, there is very nice insight that needs to be digested here.
Yeah.
Thank you. It's very nice.
Thank you.
So maybe I can ask. So what happens if you were to think about tensors as opposed to matrices?
This is a difficult question. I mean, even in the positive, yeah.
But intriguing.
Yeah, intriguing. Yeah. Should try to have a look. Yeah.
Well, thanks so much.
Thank you.